Okay, so here I'm going to prove the FTC part 2. So FTC part 2 says if you're integrating from a to b on a function f at x dx, it's big F at b subtract by big F at a, where the big F, if you differentiate that, you get f at x. Okay, so in other words, the big F at x is the antiderivative of the small f at x. Okay, so let's consider a function. Okay, so let me let g at x equal to c2x, okay, c2x f at t dt. So if I differentiate that by FTC1, the fundamental theorem of calculus, I get this. Okay, look at this and this, you can see that I can claim then the derivative of such a function is f prime at x, which means g at x is big F prime at x, so antiderivative of, so big F at x plus constant. Okay, now using integral properties, let me integrate that from a to c and c to b. Okay, I'm gonna switch the order c to a and put a negative in front using, again, integral properties. Okay, and I'm gonna put this as limit x approaching a, c to a, and here I'm gonna put limit x is approaching b, c to x. Oh, sorry, I meant x here. Okay, x is approaching a, and just replace that with a variable. Okay. Now this part here I can replace with limit x approaching a, big F at x plus c. This here I can replace with big F at x plus c. Here the limit is approaching c, b though. Okay. So we get this, right? If you take the limit on the c here, it just become minus c. It doesn't do anything. Okay, and here it just become also c, positive c. So note that these two cancel out. Okay, and that is equivalent because the big f at x is continuous, right? Continuous and smooth. It's f at b. Okay, that's f at b, and that right there is minus. So minus is from there, f at a. Okay, so that's the proof of the integral from a to b on the small f at x dx is equal to this. This is a proof of FTC2.